Hello everybody, today welcome to our class for geometry, and we will be talking about isosceles triangles and also equilateral triangles, and most of you guys are probably familiar with those according to maybe what you took back in middle school or even before that. So let's go ahead and try to come up with some formal definition so then that way we can apply it to our geometry class. So the first thing we're going to do is we're going to define those two terms, what is an isosceles triangle and also what is an equilateral triangle. Then afterwards, we're going to look at some of the theorems that will go along with each one of those. More specifically, something called the isosceles triangle theorem, and then there should be something for an equilateral triangle as well. And finally, we'll go over the last term, which is known as equiangular. All right, so go ahead, let's go and get started. So the first part is we're going to go ahead and define the following then, okay? And a triangle is considered an isosceles if at least two of the sides are equal or congruent to each other. So as a restate, that means that if you have a triangle ABC and it's considered an isosceles triangle, then what I can get from it is that AB is equal to BC, or you can say AB, the length, is congruent to BC, the length. And similarly, then, if I look at a triangle and I call it equilateral, then that means that all the sides are going to be congruent to each other. So again, as a restate, if ABC is equilateral, then that means that AB is equal to BC is equal to CA. And also you can say that their sides are going to be congruent by AB is congruent to BC, which is congruent to CA. So you can see from the picture below for each one of those. Now, a few notes that you should understand is that number one, that equilateral triangles is also considered isosceles because according to my definition, an isosceles triangle is at least two sides that are going to be congruent to each other, and hence equilateral is three sides. So yes, that means that they are subset. One is a subset of the other. Next is that there are some names that goes along with this. In the isosceles triangle over here, right, we can say that AC, which is this length over here, that is what is known as the base. So we can go ahead and call that the base. But whereas, let's see, angle A and angle C, these two angles that are next to it right there, those are what is known as the base angle. And finally, for the length of those sides of AB and also BC, the two sides that are congruent to each other, we call those legs then. Okay. For equilateral triangle, well, there's no special name for all of them, so we'll just go ahead and let that one be. Let's go ahead and think about what can we do or what can we conclude about these characteristics then. If you know that you have an equilateral triangle, or if you know that you have an isosceles triangle, what are the conclusions? Well, we know the sides are going to be congruent according to definitions, but we can probably say something about their angles too, because if you look at inspection-wise, let's say this angle right here, I feel like that angle is going to be the same as this angle over here. And in the case of an equilateral triangle, if I'm looking at the angles, all those three angles are probably going to be equal to each other or congruent to each other as well. So my conclusion is as following, and this is basically going to be the theorem then. Theorem 5.4, which is also known as the Isosceles Triangle theorem, ITT for short. If two sides of a triangle are congruent to each other, basically meaning that you have an isosceles triangle, then the pair of their opposite angles are going to be congruent to each other. So once again, as a restate, in the triangle ABC, if AB is equal to BC, which is definitely shown in this picture right here, then what I want to do is I want to prove that their opposite angles are congruent to each other. So that is these two guys right there are going to be congruent to each other. So let's go ahead and look at the proof for this so you can see how this actually works out. What I'm going to do is I'm just going to go ahead and take the triangle and I'm going to flip it. Okay, I am going to rotate it, I guess. That's probably a better terminology. Okay, so B is still on top if you kind of like rotate it by 180 degrees. So when I rotate it, then that means that C is going to go to where A is located. And that means that also A is going to go to where C is located. So basically, we're just kind of like flipping it over then. Okay, so that's going to be my end result after I flip it. Well, if I just flip the triangle, then that means that the characteristics should still stay the same. So that is to say that you still have BC, which is congruent to BA over here. Now, looking at those two triangles, I can probably say that those two triangles are going to be congruent because it's the same triangle, and I haven't altered anything in any way whatsoever. But by proving those two triangles are congruent, then maybe then I can show that their corresponding parts are going to be congruent, hence the angles that we're looking at. So here we go. Let's go ahead and see what we can come out of it. Judging by the two triangles right here, we can go ahead and say the following. We can say that AB is congruent to BC. Okay, so these two sides are going to be congruent to each other. Then we also have this angle B, which is going to be congruent to itself by reflexive property. And finally, we can say that this length right here is then congruent to this length. So if you look at what I marked, and in terms of like what I'm aiming for, I'm probably looking at SAS for those two triangles then. Okay, so here's the write-up then. First, we're going to go ahead and say, like we said, number one, AB is equal to BC. Okay, and that right there is just going to be given because it's literally right there. Now, this is the rare one moment that this is going to come out. BC is equal to AB, and that's the next part right there. Oh, sorry, actually, I kind of skipped a step. So let me go ahead and erase that because I don't want to go in that order. Okay. Next, after we prove the side, right, I'm going to go for the angle part. And the angle that I was looking for was angle B is congruent to angle B. So that right there is going to be the reflexive property. Okay. And finally, we're going to go ahead and look at that last side because what we're doing, as we said earlier, is side, angle, side. We're doing an SAS proof over here. So the last side is to say that BC is equal to AB. Now, technically, that is a given too, but if you want, I feel like we can get a little fancy here and we can say that it's also the symmetric property because if we took step one right there and flipped it over, it's going to be that. First time we ever see symmetric property in play, I want to try to use it if possible. Well, anyhow, there you go. Now that we know that that's true, then we can conclude that those two triangles are congruent to each other. Triangle BAC is going to be congruent to triangle BCA because of SAS. And because the two triangles are congruent, then now we can say that their corresponding parts are congruent, which will be the angle A is going to be congruent to angle C because I'm looking at this guy right here being congruent to this side. You could say the other way around too, but nonetheless, it's going to get the job done. So CPCTC. And there you go. That's going to be our proof then. Is the converse of this true? Meaning if I flip the if and then statement, is it still going to be the same thing? That is to say, if the angles are congruent, then will the opposite sides be congruent? And I like to think, yeah, that actually is going to work in this case as well. So that is going to be our next theorem, which is theorem 5.5, the converse of the isosceles triangle theorem. So here we go. Like we said, if two angles are congruent to each other, then their opposite sides are congruent to each other. And here's the restate once again, and the picture below. So this time I know the angles are congruent, and I want to prove that the sides are congruent. My guess is you probably are going to do a proof that's going to be very, very similar to the previous one. Well, without having to actually write the proof, because I think you guys can kind of see how this is work, let me kind of lead you into it and maybe you can write it yourself. What I'm going to do is, just like before, I'm going to take the triangle and I am going to flip it around. Okay, I'm going to reverse it, rotate it, whatever you want to call it, right? So then that ways, the bottom side, if I flip it, then it becomes CA instead of AC. So these two guys are probably still going to be congruent. What am I kidding? It is. They are still going to be congruent. I'm still trying to prove that this is equal to this. Look at the two triangles. How are they congruent to each other? Well, if you can see it, great. If you cannot, maybe I can give you a small little hint by doing this. Okay? And maybe then you can try to write your proof and see how this works out. What you can do is also use the previous to help you write the proof for this one. All right? All right, so now a few more items and then we're pretty much done. There are three types of triangles that we can categorize. The first one, this is what is known as an equilateral triangle, which means that all three sides are going to be equal to each other or congruent to each other. If only two sides are equal to each other, we said that those are isosceles triangle. If none of the sides are equal to each other, we call them a scalene triangle. That is to say that all three sides are going to be different. So one is like 5, the other one is 10, the other one is going to be 16 or something like that. And that would be an example of a scalene triangle. Now 5, 10, 16 triangle, that technically isn't going to work. And we'll prove that in the future, but just to give you a numerical example. And the last type is called an equiangular triangle. Okay, an equiangular triangle is defined that all 3 angles are congruent to each other. Well, thinking about what we just said about like isosceles triangle and the isosceles triangle theorem, I like to think that maybe the equiangular triangle and the equilateral triangle, there will be some relationship. That is to say, if you have a triangle that is equilateral, would it be considered equiangular? And the other way around, if it's equiangular, is it going to be equilateral? And I think, yes, the answer is going to be the case. The answer is yes. So those right there, those are what is known as the following corollaries, as we said. Corollary 5.4.1, which states that, yes, if you have an equilateral triangle, they are equiangular. And then the next corollary says that if it's equiangular, then you have an equilateral triangle. Corollary is kind of like a postulate in a way. It's kind of like somewhere between a postulate and a theorem. What does that mean? It means that it is something that is provable, but it's so simple that you probably don't even think about writing the proof. You can write the proof if you want, but it's provable, right? But whereas postulate is like something that we kind of take for granted for because it's so simple that there's really no proof for it. So this is kind of like somewhere in between. Your proof is probably going to be like 2 or 3 steps. That's where corollary comes from, or in some cases they call it lemma. But there you go. I think those are going to be our scenarios then for today. So let's look at this last example just to kind of show you how this works out. Basically applying everything that we learned, right? So given on the side right here, you have a triangle, and then you have kind of like, well, 2 triangles in this case. We know that triangle ABC is an isosceles triangle with base B. So that's the first part that is going to be given. And I also am given that AD bisects BAC. So let's go ahead and mark those up first of all, so we can see how this actually proves works. So the first one, let's go ahead and draw that. ABC is an isosceles triangle. So then that means that if I were to go by the definition of isosceles triangle, and I know that BC is given as the base, then that means that most likely these 2 guys are going to be congruent. So that is what I can extract from the information in the first part. Now, the second part says AD bisects BAC. So then that means for this one, let me go ahead and maybe use a different color. AD is going to, AD is going to bisect BAC. So then that means that is going to say that these 2 angles are going to be equal to each other or congruent to each other. Looking at the markings that we have, we probably want to show that the 2 triangles are congruent to each other. And you can probably see it by now from those practice problems that we did a while back, that we can probably put this over here as well. Then as a result, the 2 triangles are congruent to each other by SAS. And that will then allow me to prove that BD over here is going to be congruent to DC, which is over here, hence making D my midpoint then as of BAC. So the proof is, the procedure is as following. I am going to go ahead and prove triangle BAD is going to be congruent to triangle CAD by SAS. And then afterwards, we're going to go ahead and say that BD is going to be equal to DC by CPCTC. And finally, we can then say that D is the midpoint of BC by the definition of midpoint. So that right there is going to be our outline of the proof. So just to not waste some time, I'm going to go ahead and show you that proof right here. So you can probably go ahead and pause the video and take a look at it if you want. But that's basically the idea then. All right.